In this lecture session on quality by experimental design, I am going to discuss in detail a particular experimental design which is referred to as the completely randomized experimental design. Now, completely randomized experimental design is your starting point. That means what you find that whenever you believe in say the concept of statistical design of experiments, so your starting point is this completely randomized experimental design. Only in certain conditions what you do, that means you refer to certain variations in randomized experimental design. So, the original design you must know, and then you also must know that in a given situation you may have to opt for a variation of completely randomized experimental design. So, in this lecture session let me explain in detail the completely randomized experimental design. Among many types of designs recommended, a completely randomized design is the most simple one, and that is why you say that in any experimentation exercise this is your starting point. In this design, treatments are randomly assigned to the experimental units, and each unit has an equal chance of being assigned to any treatment. That means this is essentially we say that the randomization principles you have to follow, and while you follow this randomization principle, you need to follow these principles completely. Assignment is made through the use of random number table. Okay, I hope that you are aware of what is a random number table. Those who were not aware of random number table, please refer to random number table, and how to use the random number table we will explain right now. So, but you should refer to the random number table, and you also must know that how these random numbers are generated. So, here whenever you refer to a random number table, what we assume that these random numbers are generated from the uniform distribution. The uniform distribution is referred to as that many a time it is referred to as the distribution with maximum ignorance. That means even if you do not have say the data, the past data at the initial stage in the beginning, you may assume that the random variable is uniformly distributed, and as you get the data, you can revise your assumptions related to the distribution. Now, here is an example how to use the random number table. Suppose there are 4 treatment combinations. Already we have defined what is the treatment combinations, denoted as A, B, C and D, and each treatment is replicated 3 times. Okay. So, replication principles already we have explained. Hence, there are a total of 12 experimental units. For assignment of these units randomly, 12 random numbers are required. Suppose the following 3-digit random numbers are selected from the random number table. Is it okay? This is available. Okay. So, random number table. So, you will find in any textbooks on in statistics, you will find that in the appendix a random number table is given. So, these are the 3 values 984, 618 and so on 240. So, these 12 values you select. Treatment A is assigned to the first 3 numbers, treatment B the second 3 numbers and so on. Once these numbers are ranked from smallest to largest, these ranks correspond to the experimental unit numbers. Thus, the experimental unit 1 is assigned to treatment C, experimental unit 2 to treatment B and so on. So, this rule you follow, right. Thus, the time order of the data collection and experimentation is known. Okay. So, this is just a simple example. A number of merits of these designs need to be mentioned. That means, why do you opt for this one? We have been saying that given a condition, you must opt for completely randomized experimental design. So, what are the advantages? First, any number of treatments or applications can be used in this design. Is it okay? Any number. Different treatments need not be replicated the same number of times, making the design flexible. Is it okay? So, this is point number 1. What is the next the merit? Sometimes it is not feasible to replicate treatments an equal number of times. This is because of many reasons. In fact, time could be a constraint, resource could be a constraint, there could be many other reasons. Suppose the treatments represent different machines. Machine 1, because of its capacity and resource advantages, may run as many times as desired. Is it okay? This is a practical problem we are highlighting, whereas machine 2 and 3 cannot be run that frequently. Okay. Whereas treatments 1 can be replicated 10 times each, treatments 1 and 2 can only be replicated 5 times. This experimental design is an unbalanced one. Is it okay? When all treatments are replicated an equal number of times, the design known as a balanced one. Though always we prefer a balanced design as a balanced one, but due to some practical problems, so many a time you may not have the balanced experimentation. So, you go for an unbalanced experimental design. Is it okay? So, this is unavoidable in majority of the cases. However, in a randomized experimental design, the precision of the experiment may be at a low level if the experimental units are not uniform. So, this is point to be noted. The principle of blocking may be used to work on these problems. Till now, we have not mentioned about say the blocking. So, the first you start with completely randomized experimental design, and if you find that the precision of the experiment is at a low level, then the next best option is that you go for the block design. Okay, so randomized block design. So, the statistical procedure used to analyze the experimental unit, this is a very important point to be noted. Now, what is the statistical procedure? This statistical procedure is known as the analysis of variance, or in short ANOVA. So, when we take up the numerical problems, we will construct the ANOVA table. Is it okay? So, against any such experimentation you carry out, so there must be analysis of variance. Is it okay? So, what is this ANOVA? This ANOVA determines the effects of the treatments as reflected by their means through an analysis of their variability. So, in this technique, what you do? The total variability in the observations is partitioned into two components: variation among the treatment means, or the treatment sum of squares. This is the term we use, treatment sum of squares, and the variation among the experimental units within treatments, that is the error sum of squares. Is it okay? So, two terms we use, one is the treatment sum of squares and the second one is the error sum of squares. So, the total sum of squares, that is SST, is equal to treatment sum of square SSTR plus error sum of square, that is SSE. Is it okay? So, this is relationship. So, what we try to do, that the mean squares for the treatments and for the error are obtained by dividing the corresponding sum of squares by the appropriate number of degrees of freedom. This number is 1 less than the number of observations in each source of variation. Is it okay? So, this rule we follow. For example, for a balanced design, we know what is a balanced design with P treatments, each with R replications. The total number of observations is R into P. It's clear? The total variability has Rp minus 1 degrees of freedom. The number of degrees of freedom for the treatments is P minus 1. For each treatment there are R observations, hence R minus 1 degrees of freedom applied toward the experimental error. The total number of degrees of freedom for the experimental error is therefore P into R minus 1. It's clear? So, this rule we follow. Now, what are the notations we use? So, let me first use these notations. P is the number of treatments. We already know that what is a treatment. R is the number of replications for each treatment. We know that why the principle of replication you have to follow. Yij, the response variable value of the jth experimental unit, okay, that is assigned treatment I. Is it okay? So, this is the treatment is I, that means I varies from 1 to P and j varies from 1 to R. It's clear? So, what is Yi? Sum of the responses for the ith treatment, that is sigma j equals to 1 to R Yij. It's clear? What is Yi dot bar? That means the mean response for the ith treatment Yi dot divided by R. It's clear? What is Y double dot? That is grand total of all observations, that is sigma I equals to 1 to P, j equals to 1 to R sigma Yij. And what is Y double bar? That is the grand mean of all observations, that means Y double dot divided by R into P. So, this is this is the notations we use, and we have explained which notation means what. The data collection formats for P number of treatments with R number of replications for each along with the notations used for means are shown in table. So, what is this table? So, we will show you the table in fact. So, with the given notations, the total sum of squares is computed is this one SST, that is the total sum of squares. Is it okay? And the treatment sum of square is given by this, right, sigma I equals to 1 to P Yi dot square divided by R minus C, where C is a correction factor. So, that correction factor is Y double dot square divided by R into P. So, the error sum of squares is given as SSE equals to SST plus SSTR, and the mean square for treatment is given by this one. Is it okay? So, SSTR divided by P minus 1, and the mean square error is given by MSE to SSE divided by the degrees of freedom, that is P into R minus 1. Okay. So, this is the standard formulations we have. So, in experimentations, what you do for different treatments considered, it may be desirable to know if the treatment means are a function of treatments, or in other words, if the values of the treatment means as obtained are varying from one treatment to another. Is it okay? So, the variations are to be traced essentially. Hence, it is desirable to test the hypothesis that the treatment means are equal against alternative hypothesis that at least one treatment mean is different from the others. Is it okay? So, the treatment mean is actually your result, and that you are trying to test. Is it okay? So, whether in the treatment wise the mean value the differs or not. Thus, the hypotheses are mu1 equals to mu2 is equals to mu p, and what is the alternative hypothesis? H1, there is at least one treatment mean mu is different from the others. Is it okay? So, in this case the test statistics F statistic is computed as F equals to mean square treatment divided by mean square error. Is it okay? With P minus 1 degrees of freedom in the numerator and P into R minus 1 degrees of freedom in the denominator. Is it okay? So, this is the table you have. You have the treatment 1 and 1, 2 up to P treatments you have. Each treatment is replicated R number of times. Is it okay? And then this is the way you collect the data Y11, Y12, Y1R, this is Y21, Y22, Y2R. Is it okay? Look at this table. I think all the notations are made very clear the notations which we have used already. So yp1, is it okay, it's the pth row, and this is yp2 and similarly ypr. So you get the sum, that means the sum against the first row, is it okay, whatever may be the value of r, that's a variable, that's why it is dot. So this is y2 dot and this is yp dot, is it okay. So when you add them, that means it becomes y double dot. It's clear. So sum, and then you get the mean. So you get the mean, that is y1 bar, this is y2 bar, yp bar. So this is referred to as the mu1, mu2, mu p. Is it okay? Now you are comparing whether they are equal or they are unequal. Is it okay? So if you say equal, then you say it is the null hypothesis. If you say that at least one is different from all others, that means this is the alternative hypothesis, H1. Is it okay? So for a chosen level of significance, say alpha, say 0.01 or 0.05, the critical value of f obtained from the table is denoted by this. Okay. So if the computed test statistics, the null hypothesis is rejected, and we conclude that the treatment means are not all equal at the chosen level of significance. Is it okay? This computational procedure is known as analysis of variance. The typical format of an ANOVA table for this experiment is shown. So I have already mentioned that what is ultimately, now you need to analyze the variance. So the analysis of variance is very important. So you create the ANOVA table. So what is the typical format of an ANOVA table for a completely balanced randomized, say, the design? So the source of variations, basically the treatments or the error and the total. Degrees of freedom is p minus 1, error is p into r minus 1. So the total degrees of freedom is rp minus 1. Is it okay? So if you add this, you will get rp minus 1. Sum of squares is SSTR, SSE, this is SST, fine. Then the mean square is SSTR divided by the degrees of freedom. Similarly, mean square error is sum of squares of error divided by the degrees of freedom. And then f statistics is, this is MSTR, okay, the treatments divided by MSC. Is it okay? So this is the f statistics you compute. If the null hypothesis is not rejected, there is no significant difference among the treatment means. If the means, it means that the response variable is not affected by any particular treatment, and hence the most cost effective treatment should be selected. So that is your conclusion. Is it okay? So what do you try to do? That means when you look at the ANOVA table, is it okay, as well as the results from your hypothesis testing. So if you conclude like this, that means what do you conclude? That means that the most cost effective treatment I need to select. You have already considered the p number of treatments. Is it okay? So which one is the most cost effective? If the null hypothesis is rejected, management might be interested in knowing which treatments are preferable among p number of the treatments. Each sample treatment mean is a point estimate of the population treatment mean. Fine. If the interval estimates are desired, a 100 into 1 minus alpha percentage confidence interval for the treatment mean can be computed. We have been telling all the time, we have been preferring, the interval estimate to, say, the point estimate. So here, how do you get this the interval estimates as a confidence interval for mu I, that is already yi bar you have computed, and this is the the assuming the t statistic. So the t alpha by 2, that is alpha by 2, and this is the degrees of freedom p into r minus 1 into root over say ms of error, okay, mean square error of error, and this is r, where t alpha by 2 p r minus 1 is the t value for a right tail area of alpha by 2 and p minus 1 degrees of freedom. Is it okay? So, the quantity is this one, that is root over MSE by R, represents the standard deviation of the sample treatment means y I dot bar. In order to know if one treatment is preferable, this is the standard procedure I am explaining for all design of experimental so the methods we use or we employ. In order to know if one treatment is preferable to the other, a 100 into 1 minus alpha percentage confidence interval for the difference of the two treatment means needs to be computed. The confidence interval for the difference between two treatment means is this one, mu I1 and mu I2. Is it okay? So, it is given by this one. Is it okay? So, these expressions you have, right? You just take the difference only, where this value is the t value for a right tail area of alpha by 2 into p into r minus degrees of freedom, and this quantity, that is root over MSE by R, represents the standard deviation of the difference between the sample treatment means is this one. Is it okay? So, this you need to consider. There will be fixed and random effects, as we have been telling you that the fixed and random effects are used in the context of analysis of variance and the regression models. Essentially, you assume a linear regression model initially, and these fixed and random effects refer to certain types of statistical model. Almost always researchers use fixed effects regression or ANOVA, and they are rarely faced with a situation involving random effects analysis, but in certain cases you may have to opt for. In a fixed effect ANOVA refers to assumptions about the independent variables and their error distributions. An experimental design is the easiest example for illustrating these principles. Usually, the researcher is interested in only generalizing the results to experimental values used in this study. So, generalization is your goal. For instance, a study on the effect of firing temperatures specifically chosen by the experimenter here in this case, okay, firing temperature using 100 degrees Celsius, 125 degrees Celsius and 150 degrees Celsius on density of bricks. This is a case where a fixed effect ANOVA may be appropriate. In this case, the extrapolation is to other studies or treatments that might use the same values of the temperature factor. That means, when the extrapolation is required, maybe you may go for say the random effects analysis. So, the 100 degrees Celsius, 125 degrees Celsius and 150 degrees Celsius, these three temperature levels you consider. Now, in this case, the experimenter wishes to test the hypothesis about the treatment means, and his or her conclusion may apply only to the factor levels considered in the analysis. Is it okay? That means you are saying that this system will continue, only these three levels I need to consider. The conclusions cannot be extended to similar treatments that are not explicitly considered. Is it okay? So, then in that case you have to go for the random effects model. Is it okay? So, this is here we are referring to fixed effects model. Is it okay? So, so the one particular case we are referring to, that is the Fisher's LSD procedure, comparing pairs of treatment means. An approach suggested by statistician R.A. Fisher called the least significant difference method, or LSD, least significant difference method, or it is also referred to as the Fisher's LSD, is to first test the null hypothesis that all the population means are equal using analysis of variance. We have already referred to ANOVA, analysis of variance table. So, the null hypothesis is expressed as this one, mu I equals to mu j, and the alternative hypothesis, that is H1, that is mu I is not equals to mu j for all I not equals to z. If the analysis of variance is not significant, then the null hypothesis is rejected, implying significant differences among the means. If the analysis of variance is significant, okay, Then the means are compared with one another with an F statistics expressed as this one. So, this is your F statistics, and that statistics is given by this one, yi dot bar minus yj dot bar divided by root over mean square error into 1 upon ni plus 1 upon nj. Is it okay? So, this is the procedures, that means two-sided alternative. So, just refer to this particular case, right. So, you may use this particular notations, and n is the total number of observations, ni and nj are the number of observations for ith and j treatment. Later on, when we refer to a particular example, it will be made very clear, and this is the mathematical expression for LSD. Is it okay? So, this is called the least significant difference, or LSD, right. So, many a time we do that. Now, before I conclude these sessions, let me explain one particular examples. Is it okay? Related to design of experiment. A company has to deliver its goods to distributors throughout the country. 3 transportation companies have offered their services for this purpose. To test the efficiency of these 3 transporters, the company randomly assigns its outgoing product shipments to them and determines the degree of lateness as a proportion of time allocated for delivery. That means this becomes your the response variable. Table 3 depicts the values of the degree of lateness of the transporters for 5 shipments. So, how many transporters you have? 1, 2, 3. Is it okay? And this is basically 1, 2, 3, 4, 5. Okay. So, depicts the values of for 5 shipments, that means 5 replications. So, the corresponding data you have, that means these are the values of y, that means response variable, and what is the response variable over here? That is the lateness, okay, degree of lateness. So, first whenever you say this is the response variable, so you have to define it and you must specify how to measure them. That means here we are assuming that there is a measure, and you know which data are required to calculate this value, and this is suppose 0.04, and then this value is 0.15. Okay, which one is preferable, whether 0.15 or 0.04? So, those details you must know, right. So, how to compute the value of y, that also must be explicitly specified. So, this is the value. Now, the question is there a difference in the mean degree of lateness of the 3 transporters? Is it okay? That means 3 treatment combinations. Test at 10% level of significance. Find a 95% confidence interval for the mean degree of lateness of transporter 1. When the transporter 1, you have collected data 5 times. Is it okay? So, you have a mean lateness, right. Now, how to determine the 95% confidence interval for the mean degree of lateness for transporter 1? Is it okay? Treatment 1. Find a 90% confidence interval for the difference in the mean degree of lateness of transporters 2 and 3. So, I think is where this part already we have discussed, and the formulations are already given. Now, when we explain the problem, that means you can relate this problem with the formulations. If there is a difference in their means at 10% level of significance, that means first what you are trying to do, you assess the performance of transporter 1, and then in next time what you try to do, that means is there any difference in the performance between transporter 2 and transporter 3. Okay. So, you create this analysis of variance, like the treatments, the degrees of freedom will be p minus 1, that is 2, error is 12, and the total is 14. Sum of squares, you apply the formula, okay, you get all these values, and the mean square is this one, right. When you divide this value by the corresponding the degrees of freedom, and ultimately F statistics you get. Is it okay? So, you are applying this formula, and alpha is 0.10, corresponding f value you get like this 2.81, which is less than f equals to 23.57. We conclude 57. We conclude that there is a difference in the mean degrees of lateness among the three transporters. So that is your conclusions. So the mean degree of lateness for transporter 1 is denoted by mu1. The 95% confidence interval you calculate by applying the formula. So this is the confidence interval. The mean degree of lateness for transporters 2 and 3 are mu2 and mu3. These notations we use. The 90% confidence interval, again you compute for the difference between the mean degree of lateness of transporter 2 and transporter 3. So how do you calculate this? You apply the formula. So this is the confidence interval, that is 0.0409 and 0.0871. Okay, so this is a typical example. Please go through it, and I hope that you have understood that how important this design of experiment is, and in subsequent lecture sessions as a part of assignments I will give you several examples on the design of experimental or design of experiment methods. Is it okay? There are many methods, only one particular method till now we have discussed, and please go through these numerical problems already discussed. Okay, so you refer to this particular textbook. There are many other examples we will be dealing with in subsequent lecture sessions.